Dear students, I, Mr. Vishal Shah, Assistant Professor, Krishna Institute of Pharmacy, Karad, once again welcome you all to this my YouTube channel. In this video, we are going to discuss about the chapter of pharmaceutical organic chemistry, that is the cycloalkanes. In this video, we are going to study about the Baeyer strength theory. In previous few videos, we have covered the conformations of cyclohexane as well as the different methods and chemical properties that are shown by the cycloalkanes. So let's begin with our today's session. If you are coming first time to this my YouTube channel, watch my previous videos related to the pharmaceutical organic chemistry also. If you like the content of this my channel, then please subscribe to my YouTube channel. Also you can share with your friends. So let's begin with our today's session. Now, before starting with our today's session, just we will see what are the learning outcomes of this session. Means after watching this video, what you should understand. After this session, students will be able to explain about the Bayer's strength theory. Also, they should be able to explain the advantages as well as the disadvantages, or you can say limitations, advantages and limitations of Baeyer strength theory. So let's see what is the meaning of Baeyer strength theory, what information this theory should or it gives. So Baeyer strength theory, which is also known as angle strength theory, this theory was proposed by scientist Baeyer. That's why this theory is known as Bayer's strength theory. This theory gives information related to the stability of cycloalkanes as well as the reactivity of cycloalkanes. Van 't Hoff and Liebel proposed the tetrahedral geometry of carbon. Now we are familiar with the molecule methane. Methane molecule, which is having one carbon atom and the 4 hydrogen atoms that are attached to it. Such a type of carbon atom is known as tetrahedral carbon atom. So the tetrahedral carbon atom, which is having the bond angle of 109.28, which is also referred as 109.50. So when the carbon is having tetrahedral geometry, the bond angle between hydrogen carbon hydrogen in the methane molecule is having the 109.28 degree. So whenever carbon is having tetrahedral geometry, always it will be having the bond angle of 109.28 degree. If we consider the ethane molecule, different alkane molecules which are having the tetrahedral carbon atom, so in that case all these molecules are having hydrogen carbon hydrogen bond as a 109.28 degree. But what Baeyer has observed, Baeyer observed that different bond angles are present for different cycloalkanes and also observed some different properties and the stability. If we compare the stability and reactivity of alkanes like methane, ethane, propane, they are somewhat closer to each other. Also, the geometry of the carbon atom and hydrogen atom is same in all these molecules. But if similar things that is observed for the cycloalkanes, the bond angles that are present in the cycloalkanes that are different, and also they show different properties, wide variety of properties that are shown by the both or the different cycloalkanes. So this is the thing that he has observed. And on the basis of this, he has proposed one theory which is known as the angle strength theory or Baeyer strength theory. This theory gives us information about the amount of strength that is present on the different carbon atoms that are involved in the cycloalkanes. The theory explains important thing, that is the reactivity and stability of cycloalkanes. So if someone wants to explain the stability and the reactivity of cycloalkanes, the answer for that is Baeyer strength theory. So actually 3 different theories are there which explains the stability and the reactivity of cycloalkanes. One is the Baeyer strength theory, Cullinan-Moffat's theory, and the last theory that explains the stability and reactivity of the cycloalkanes is Saxe-Mauer theory. So these are the various theories which explains the stability and reactivity of the cycloalkanes. The first theory that was put forth by the scientist, that is known as the Baeyer-Strain theory. Now what he has done, Baeyer proposed that optimum overlap of atomic orbitals is achieved for the bond angle of 109.5. Means if carbon has to maintain the tetrahedral geometry, then optimum overlapping is possible in that case, and the bond angle is maintained at 109.5. In short, it is the ideal bond length bond angle for alkane compounds. Effective and optimum overlap of atomic orbital produces maximum bond strength as well as the stable molecule. Means if carbon-carbon or carbon-hydrogen bond, it maintains the optimum overlap, which leads into the formation of maximum bond strength, and the tetrahedral geometry of that particular carbon is maintained. If bond angles deviate from the ideal means what here, 109.28 or 109.5 degrees, then the ring produces certain strain. Means the carbon atoms that are present in the cycloalkanes, they are not in comfortable position because some amount of strain is present on that particular carbon atoms. Now what he has given equation, that is the higher the strain, higher the instability. Means you can say less stable that particular compound is. If strain increases, the stability of that particular compound decreases. So this is the vice versa relation that he has proposed. How he has proposed this relation, just we will see with the help of few examples. Now higher strain produces increase the reactivity and increase the heat of combustion. These are the another two factors due to the presence of higher strain. Though reactivity increases as stability decreases, and it also increases the heat of combustion. We will see what is the meaning of heat of combustion in latter part, but here you can remember that due to the higher strain, it produces the increased reactivity and it increases the heat of combustion. Now what Baeyer has proposed, any deviation of bond angle from ideal bond angle value, you know that ideal bond angle value is 109.5, that will produces a strain in the molecule, and higher the deviation from that ideal bond angle, lesser the stability. So this is the statement that he has proposed. So any deviation of bond angle from the value, that is the 109 degree, will produces the strain in the molecule, and if this deviation is more, then lesser will be the stability. Now how to calculate that deviation, that will also I will explain. But whatever the things that Baeyer has proposed, he has proposed this theory depending upon some assumptions. Now what are these assumptions? What he has considered, that all ring systems are planar in nature. What is his assumption? So whatever the cycloalkane molecules are there, he has considered it as a planar. Means whatever the carbon atom and hydrogen atoms that are present in cycloalkanes, they lies in the one plane like benzene or aromatic compound. So that he has assumed. Also he has assumed that deviation from normal tetrahedral angle results into the unstable cycloalkanes. Then large ring systems involve negative strain, hence they do not exist. Now what is the meaning of large ring systems? Means ring systems more than cyclohexane. So these ring systems involve the negative strain, and according to him, these particular rings does not exist in the universe. The bond angles in cyclohexane and higher cycloalkanes like cycloheptane, cyclooctane and cyclonone are not larger than 109.5 because the carbon rings of those compounds are not planar, that is not flat, but they are in the puckered or you can say wrinkled position. So these are the various assumptions that he has assumed, and on the basis of these assumptions he has proposed this Baeyer-Strain theory. Now these assumptions are helpful to understand instability of cycloalkane ring systems Here just you have to remember that cyclopropane is more reactive than cyclobutane and cyclopentane. Means cyclopropane is less stable. As we know that what he has proposed, that higher the deviation, instability will be more or reactivity will be more. So cyclopropane is least stable among this particular series. Now we know the ring of cyclopropane is triangle in nature. All the three angles that are present in cyclopropane are of 60 degree in place of 109.5, which is the normal bond angle for carbon atoms. To adjust them into the triangle system, here you can see this is the structure of cyclopropane. Now as you see, there is another geometrical theorem also. If all the bond lengths of the triangle are same, then the angle between these two carbon atoms, these three carbon atoms, will be 60 degree. So instead of 109 degree angle in cyclopropane, the bond angle is 60 degree. Now in the same manner, cyclobutane is a square. Here you can see the figure of the structure of the cyclobutane, which is a square, so that the bond angles are at 90 degrees Celsius instead of 109. To adjust them into the square ring system, means here deviation from normal bond angle value is occurring in cycloalkanes. The deviation from cyclopropane and cyclobutane ring systems, then normal tetrahedral angle will produce the strain on that particular ring. The ring strain will make them unstable as compared to the molecules having tetrahedral bond angle, and so cyclopropane and cyclobutane will easily undergo ring opening reactions to form more stable open chain compounds. Now how he has calculated these particular strains, or how to calculate these particular strains? Now just we will compare that with the help of the different examples. So here we will compare the stability of cyclopropane and the cyclobutane as well as the cyclopentane also. Now as we said that bond angle in cyclopropane is 60 degree. We know that the normal tetrahedral bond angle is 109.5. Now how we are going to calculate the deviation? Deviation is equal to normal tetrahedral bond angle minus actual bond angle. Okay, so deviation is equal to, sometimes it is divided by 2 also. So deviation is equal to 109.5 degree minus 60 degree, that is the 49.5. So if we divide it 2, because two different bond angles are involved in this case, so each bond is having approximate a strain of 25 degrees in case of cyclopropane. Now this deviation is more, and that's why the cyclopropane is having the higher instability. Similarly, bond angle in cyclobutane is 90 degree. The normal tetrahedral bond angle is 105 degree. So again, with the help of the same formula, if we calculate the deviation, that is equal to 109.5 minus 90, that is equal to 19.5. Just you can remember these values. In case of cyclopropane, it was the 49.5. In case of cyclobutane, now here you can see this amount is reduced. Means the cyclobutane is having the less strain as compared to the cyclopropane. That's why it is more stable. Its reactivity is less as compared to the cyclopropane, and the deviation in cyclopropane, and as we know, deviation in cyclopropane is 49 and deviation in cyclobutane is 19.5. The deviation is higher for cyclopropane and cyclobutane. That's why cyclopropane is more prone to undergo the ring opening reaction. Similarly, we can calculate it for the cyclopentane, which is having a bond angle of 108. Then if we calculate the deviation, it becomes 1.5. So less deviation is present in the cyclopentane. So here deviation is 1.5. So now in this next video, we will see the further part, how these particular deviations are related to the stability of that particular cycloalkane. If you like the content of this video, then like, share and subscribe to my YouTube channel. Thank you.